Well, hi everyone, and welcome to this a wonderful Math Wednesday. And I remain your faithful math servant, Mr. Jennings, and I appreciate you all showing up for your learning. Here we are going to learn about some factoring strategies and some special factoring. I thought about calling it snowflake factoring, but that seemed a little boomer to me, so we're just going to leave it as special factoring. So, our goals for today is to be able to factor differences of squares, perfect square trinomials, and to always remember to remove the common factors first. So you can use this section right here to keep track of your learning goals during today's lesson. Now, just to review, we want to expand these fellows or these folks and get them into standard form. This is a review because we've been looking at expanding and simplify to get standard form in past lessons. So, Tyler, what did you notice when we had x plus 3 times x minus 3? Yeah, so we have x times x. That gives us x squared, no problem. X times minus 3 minus 3x. 3 times x plus 3x. And then 3 times minus 3 is minus 9. So these middle terms will cancel out and just leave x squared minus 9. Keep that in mind for later. Keep that in mind for later. Something similar might happen with this one, right? So have y'all done this one yet? Expanding and simplifying this one? So this one here, we have 5x times 5x gives me 5 times 5 times x times x. 25x squared. 25x squared. 5x times negative 6 gives me negative 30x. 6 times 5x gives me positive 30x. It's happening again. It's happening again. And then we have minus 36 at the end. So these two terms will cancel out. Negative 30 of something plus 30 of something will always be 0. It's like I have 30 apples and then you take away 30 of my apples. Why do you need all my apples? Why couldn't you have left me with 1? Okay, so that's just going to be 25x squared minus 36. Okay, keep that in mind that this middle term can disappear when your factors start looking like that. Notice that the contents of the brackets are the same, but the signs are opposite in these cases. Okay, and now here, yeah, and that's why I said notice the lack of a b term. There's an ax squared plus c, but there's no b in the standard form there. Now these ones, if we're going to expand x plus 5 squared, you want to write that out as a multiplication. X plus 5 times x plus 5. And then we use FOIL to get x squared plus 5x plus 5x plus 25. Okay. First, outer gives us 5x, inner gives us 5x, and last gives us 25. So that simplifies to x squared plus 10x plus 25. Now let's try expanding j of x. If you're already done these, thank you for your patience as I go through for those of us that are still getting started. 3x minus 2 times 3x minus 2. Have a habit of writing these out as multiplications. If you just did 3x squared minus 2 squared, that would be incorrect. Notice that over here, the common mistake, and I'll do the common mistake in red so that you know not to do this. Well, maybe we're not being nice to red, is to say that this is equal to x squared plus 25. Okay? People just say, well, I'm going to square things, so I'm going to square that, and I'm going to square that. And the thinking is nice, but it's not so simple. It's incorrect because they're missing this term. They're missing that part that emerges when I actually expand it out nicely. So the x squared and the 25 are part of the solution, but they also need this middle term, the b term. And that's missing it. That is actually incorrect. So let's expand this one. Enough chit chat. Let's get at it. 3x times 3x, 9x squared. 3 squared is 9. X squared is x squared. And then 3x times minus 2 gives me minus 6x. Minus 2 times 3 gives me minus 6x. And minus 2 times minus 2 is plus 4. Okay? Simplify the middle terms, gives us 9x squared minus 12x plus 4. Okay, so this is just expand and simplify. Today we'll be looking at how we factor those types of things. And now 2 more examples here. What's your plan for simplifying these types of things? When we have a chain of multiplication with 3 factors, or even 4 factors. B? You distribute the 3 first? You could do that. Sure. So then it would look like this. If you distribute the 3 first, this is what it looks like. The 3 is going to distribute into one of the brackets only. Don't distribute it into both brackets. That's a common error. So B, you know to distribute it only into one bracket, right? Yeah, okay, cool. So that will create 3x plus 9 multiplied by x minus 3. And now we can expand this way. 3x squared is given here. And then we have minus 9x plus 9x minus 27. Oh, wouldn't you know it happened again. These middle terms are going to cancel out. Even though these brackets look different after B distributed that 3 into that first term, it still cancels out that middle term. Isn't that cool? 3x squared minus 27. Okay, cool. Cool. This one here, can I distribute this minus 6x into this bracket first? The way B distributed the 3 into one and only one of those brackets? Why not?
Because there's a 2 at the end of the brackets. There's something called to 6 times x. Negative 6x times x, and then negative 6x times 5. Yes.
Yeah, but as you said, there's a squared over here, right?
Yeah, which means both brackets receive the same thing.
Yeah, so this is multiplication here, right? This is multiply, and this is exponent. Exponent comes before multiply in Bedmas. So we have to do the exponent first. We're not allowed to distribute that negative 6x into that bracket yet. It's kind of protected by the exponent. If we expand the exponent with multiplication, then we could do it B's way. So here, minus 6x multiplied by x plus 5 times x plus 5. I'll show you something sneaky. Did anyone notice that I did this? I've already asked you to expand x plus 5 over here. I know that x plus 5 expands to x squared plus 10x plus 25. So I could also write here minus 6x times x squared minus 10x, plus 10x plus 25. That's the result of x plus 5 times itself. And now we could distribute that negative 6x in. Oh, hi, Will. So you need a handout. It's right here. Airmail. So now we can distribute that minus 6x in. This is my way. B, you like to put it into the bracket first. That's okay. I like to expand my brackets first and then bring my common factors in. So do it either way that you like. Just make sure that you only do it into one bracket here and not into both. And here, expanding this into that would be the same as expanding it into both places. So we can't do that. So here, this would give me minus 6x to the 3. That's when I multiply this one times this one. I have 1, 2, 3 x's, so that's x to the 3, and minus 6 multiplied by all that. Negative 6x times positive 10x gives me negative 60x squared. And negative 6x times positive 25 gives me negative 150x. How did I do 6 times 25 so fast in my head? I just imagine 6 quarters. Say, how much money do I have? $1.50. Right? So I think that's mental math people can do. Yeah. Practice turning your math into things you know well, right? 6 times 25? 6 quarters? Quarter is 25 cents. 6 of them is $1.50. Anyway, let's keep going. All right. So, one of the morals of the story today is always look for common factors first. It makes stuff easier. If I'm looking at factoring f of x on the back page, Is there a common factor there to all three of those terms in that quadratic trinomial?
Yes.
What's the common factor? 2. 2 can come out. So this is how we write the common factoring here. You're going to do 2 and then have a bracket and then divide all of these terms by 2 and make sure that those end up inside the bracket. 2x squared divided by 2 would just be x squared. 6x divided by 2 will be 3x. And 4 divided by 2 is 2. And now we want to factor that trinomial. X squared plus 3x plus 2. We want to win an x game. And this is a fairly easy x game. I want to multiply to 2 and add to 3. What numbers multiply to 2 and add to 3? 2 and 1. Yeah, okay. So 2 and 1. So we won the x game, and it looks like this. Still this 2 hangs out there. Now we have the double bracket situation with x in the front. And we just punk our 2 numbers in there, 2 and 1. And now that's fully factored. Note that there are other ways that you could factor this. You could factor it as though a was 2, and then factor it with the strategy I showed you yesterday. And that's harder. This is easier. Over here, what's our common factor for g of x? Izzy. Fantastic. 3x squared is our common factor for g of x. All of these terms have at least an x squared in them, and all of those numbers are divisible by 3. Izzy, how did you know that they were all divisible by 3? Sure. I can do also a quick test with numbers like 15. Well, 15 divisible by 3, easy. But 72, maybe your 3 times tables don't go that high. So then you add 7 and 2 and find that it's 9. And anytime you add the digits to a number together and get a divisible number by 3, then the number you were looking at was divisible by 3. So yeah, they're all divisible by 3. So we factor out the 3x squared and then divide all of these terms in this trinomial by 3x squared to get what should go inside the brackets. So 3x to the 4 divided by 3x squared, well, that had 4 factors x, and we divided by 2 factors x, so we're only left with 2 factors x. A brief review, if I have something like x to the 6 divided by x to the 3, that's the same thing as saying x times x times x times x times x times x 6 times divided by x times x times x 3 times. And this x cancels that x, this x cancels that x, this x cancels that x. So I'm left with x to the 6 minus 3 or x to the 3. Okay. So that's just your quick dividing by exponents rules. When you have the same base, you can subtract the exponents when you're dividing. And when you forget that, because you probably will, you're not like me lying there, can't sleep at night and doing exponential problems in your head, because I'm weird like that. You can remember it by expanding by multiplication, like I just showed you here. Wait, I remember there's some tricky rule for that. And then you expand it by multiplication and you see the rule. Okay. Tyler, you had a question?
Yeah. You wrote 3x squared, but it's 3x and it's a 4, not a 2.
Up here?
Is that supposed to be a
Yeah.
or is it...
Yeah, because Izzy told us that the common factor, the biggest common factor was x squared. See, there's at least an x squared in all those terms, and there's at least a factor 3 in all those terms. So we can factor out 3x squared. We couldn't factor out 3x to the 4 because there's not an x to the 4 there or there. So the largest number of x's we can factor out is 2, is squared. Okay. And now when we're dividing this, when you're wondering about that, try expanding it back once I show you what this is going to turn into. Negative 15x to the 3 divided by 3x squared. Well, negative 15 divided by 3 is negative 5. And x to the 3 divided by x to the 2 is just x. And then negative 72x squared divided by 3x squared. Well, 72 divided by 3. Anyone have that handy? 24, good. So that's 24, because 3 days would be 72 hours. Cool. So 24. And the x squared divided by x squared is just gone. So now we have a quadratic that will factor. And I want to win an x game. The x game I want to win is multiply to negative 24 and add to negative 5. What two numbers will do that? Negative 8 and 3 are my winning numbers. Ding, 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 ding. Negative 8 multiplied by 3 will absolutely add to negative 5 and multiply to negative 24. So this one factors into 3x squared multiplied by x minus 8 multiplied by x plus 3. Done, final answer. Can't be factored further. Fantastic. We just factored a quartic, an x to the 4. That's something that only grade 12s do. And we're doing it already. We can do it when there's a common factor. They can do it when there's no common factor. So don't worry. Stay tuned for more math developments in the next year of your math learning. Okay, so now, always common factor first. How are we for that learning goal? Good. Let's keep going. We also want to notice difference of squares. Difference means subtraction. And I want to show you a little picture. I'll show it to you on the whiteboard. If I have a square patio, and let's say the area of the square patio is 81, because it's 9 by 9. Okay, so the area would be 81. But I remove a square from that square patio. Let's say I take out a square like this, so that's now indented. And that's 3 by 3. Okay? So I can write that as 81 minus 9, because this one would be in area 9, and this was in area 81 before I took that square out. This actually factors. I can write this as 9 squared minus 3 squared, and whenever we have these, they always multiply out like this. 9 plus 3 multiplied by 9 minus 3. 81 minus 9 was 72. Let's see if we get 72 here. 9 plus 3 is 12. 9 minus 3 is 6. 12 times 6 is 72. Cool, eh? Why is that working that way? Let's say I reorganize this now L-shaped courtyard, or this L-shaped patio, into a rectangle. I take this bit off. So I'm going to cut that bit off and I'm going to move it down here. Notice that this is 6 long. This is also 6 long. And now this would be a further 3, like that. So this is now 9 plus 3 multiplied by 9 minus 3. See how I can just move that and make a rectangle? And get 9 plus 3 multiplied by 9 minus 3. So 81 minus 9 could be written as 12 times 6. That's why. One reason why. Okay? Let's take a look. Let's take a look at factoring differences of squares. And you can also see differences of squares all up there. I'll show you some differences of squares in a minute. Here, I notice that x squared minus 36. 36 is a square. So we could write that as x squared minus 6 squared. And in this case, I'm going to use this identity, a squared minus b squared equals a plus b times a minus b. So that's x plus 6 multiplied by x minus 6. Once you spot them, these ones are easy to take apart. And I would encourage you to test your answer by expand and simplify. When you do, you'll see that they all look like these. See up here, we were creating differences of squares here. And here. 25x squared is a square. It was 5x squared. And negative 36, well, we just saw 6 squared there. Okay? So that's why we were creating differences of squares up here. Let's go down. Keep going. So some more differences of square as examples. How are we going to deal with this one? Negative x squared plus 64. Is that even a difference of squares? Negative x squared plus 24. I would love to be able to use this pattern, but it's not really set up in the same way, is it? I have a negative square plus a square. Is that a difference of squares? A little confused, eh? That's okay. It's good. I got two ways to break the confusion. Give me A or B. A. A is rewrite it. Okay? A is rewrite it this way. 64 minus x squared. Is that a difference of squares? Is 64 a square? Yeah, it's 8 squared. And now I have 8 squared minus some number I don't know yet squared. It's a difference of squares. So this one will factor this way. 8 plus x. Oh, geez, I can't think with my brain. Here we go. 8 plus x multiplied by 8 minus x. Okay, that's way number one to conquer a problem like this. Let me show you way number two. I need more space. I'm going to open up my blank pages. Move my face. Get my blank pages open. Boop. Boop. My blank pages are right there. Doo-doo. Here they are. Okay. Negative x squared plus 64. Okay. This was, call it f of x. I can't remember which one it was. I think it was g of x. Whatever. F of x equals that. That means f of x, let's common factor out a negative 1. Negative 1 multiplied by x squared minus 64. Okay? And now it looks more like a difference of squares that we would see. I just divided both of those things by negative 1. I moved the negative 1 outside, the same way that I can remove a common factor. And that basically just flipped the signs of both of those terms. Now I have negative x plus 8 times x minus 8. And you'll find that's exactly the same thing as the other way that we wrote it over there, which was 8 plus x times 8 minus x. Okay, why are these the same? If I have x minus 8, but it's negative, well, let's distribute that negative in. Negative x plus 8, and let's rewrite it a new way, 8 minus x. 8 minus x is the same thing as x minus 8 times minus 1. So they're the same. Do the way you like. I'm not a big fan of 8 plus x times 8 minus x. I would naturally want to divide the negative 1 out so that I get the x's positive in the brackets. But this is still useful for telling me the roots of this equation. Let's keep going. How about this one? 9x squared minus 121. Is that a difference of squares? Well, is 121 a square? It's bigger than 100, so test number is bigger than 100. Sorry, bigger than 10. Yes. What is it squared? 11 squared is 121. Yeah. 110 plus 11 is 9x squared a square. Yeah. What would I have to square to get 9x squared? 3x. 3x. So this one, if you notice that that's 3x squared, 3x plus 11 multiplied by 3x minus 11. We'll factor that one perfectly. I do these in one step because I just use the pattern up here. A squared minus b squared equals a plus b times a minus b. This is the pattern that we notice. If you notice you have a square, subtract another square, then they break down that way. But here's a trickier one. 8x squared minus 50. Is 8 a square? It's a cube, it's not a square. Is 50 a square? No. Are there any common factors? What is it? Show me the number of fingers that are common to both 8x squared and 50. 2. 2 is common to both. So let's factor out the 2 first. We don't want to forget lesson number 1 of today, which is always common factor first. It always simplifies things. 2 times 4x squared. Hey, wait a minute. 4 is a square. Minus 25. Hey, wait a minute. 25 is a square as well. So that will factor as a difference of squares. That will be still 2. The 2 still hangs out there. Times 2x plus 5 times 2x minus 5. Cool. I think it's cool. Maybe you don't think it's cool yet. Let's have a growth mindset about your mathematical taste. I think I'm noted Cade as present. I need to mark Cade as absent. I'll fix that later. Okay, let's keep going. Okay, questions about differences of squares? How are you for noticing them? Not very good at noticing them, eh? Here's something that I see students doing on tests. They write out the squares on the top of their test page. They write out the list. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225.
Squaring or this like thing in general?
The difference of squares. And then once you're primed to look for squares, and you see a square subtracted from another square, then you can use this pattern. A squared minus b squared equals like the square root of a squared plus the square root of b squared multiplied by the square root of a squared minus the square root of b squared. And practice some in the textbook and bring me over if you still need help. When you still need help, that's good. Now, let's take a look here at perfect square trinomials. This is our last sort of special factoring type. It's when you factor something and it has 2 identical factors. It turns out that that thing was being squared. So here, all of these are shortcuts. If you're really confused about differences of squares, for example, you can think of the a squared minus b squared as still an a times x squared plus bx plus c trinomial, where b is equal to 0. Okay? And then if you can find numbers that multiply to c and add to 0, then you can win that x game. Your x games would just look like c 0 here, because b would be 0 for differences of squares. There's no b term in between. For perfect square trinomials, there is a special pattern that exists, and to be honest, I never look for it. And I always factor them normally, and my life has continued on just fine without worrying about the special pattern. And when I go to grade 12, I'll need to learn the special patterns for perfect cubes and perfect to the 4s and things like that, because those would be harder to factor without this special pattern. Anyway, let's just pretend we didn't know this was a difference of a perfect square trinomial, and we wanted to find numbers that multiply to 81 and add to 18. What are those numbers? 9 and 9. Whenever you get the same number like that, you can be pretty sure that this is a perfect square. Okay? So this is going to be equal to x plus 9 multiplied by x plus 9. And we can write that as x plus 9 squared. All right? Now, what's the pattern for perfect square trinomials that we're on the lookout for? If you want to be on the lookout for perfect square trinomials, then you would say, well, I know a times a would give me a squared. A times b plus b times a would give me 2ab. And then b times b will give me b squared. Okay? Let's see if this one satisfies that idea. Okay? So if it did, then we would have 2x all squared giving us 4x squared. There for that first one. 25 would be 5 squared. So I just take the square root of that and the square root of that in my head. Like, what would I need to square to get that? So 5 squared would give me 25. And then let's see. If I did 2 times a times b, okay? 2 multiplied by 2x multiplied by 5, well, that would give me 20x. Dun, 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 dun. This one, turns out I created a perfect square trinomial for you. Okay, so that one would factor with this pattern. This is what it would look like. This would be equal to 2x plus 5 squared. And that would be done. You would be that fast if you notice the perfect square trinomial. Now, let me tidy up my 5 because my 5 is really janky. I drew a 2 and then just went over it with a 5. Okay, so this was our like square root of a, our square root of c, and then we did that to find the b term. Whenever you find that pattern that is 2 times a times b, then you can write it this way: a plus b squared. Bip, 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 like that. And you're done. But I'm not satisfied because I think that's really hard to spot, to be honest. And I think you already have the tools that you need to factor that normally. So let me show you what that looks like factoring that normally on my blank pages. If I have 4x squared, and this will be a review from yesterday, plus 20x plus 25, and I first look for common factors and find none. There's no common factors here to remove. So I have to use my special factoring when a is greater than 1. I'm going to win a special x game where I take 4 times 25 equals 100. I want to multiply to 100 and add to 20. Let's see if I can do it. How do you multiply to 100 and add to 20? Sorry? Oh, yeah, 10 and 10 will do it, won't it? Yeah. See, that wasn't hard. 10 and 10. Oh, we have the same number showing up in 2 places. Maybe this creates a perfect square. So then we do this. 4x squared plus 10x plus 10x plus 25. Okay? You just decompose the middle term by these numbers. That tells you how to break up this number. Okay? Now factor this piece and that piece separately. This will be 2 times x is my greatest factor there, and it leaves 2x plus 5 plus, and here my greatest factor is 5, multiplied by 2x plus 5. Wow! And then that factors into 2x plus 5 multiplied by 2x plus 5. And that's what I would do. And then I would say, oh, it was a perfect square trinomial all along. Done. Mine is a little more work, but it's a little less fancy, mathy, parlor tricky stuff. It's just the get in there and get her done. So I like get in there, get her done. And that's how you get in there, get her done. So, yeah. Now, you have textbook practice problems. Try those. Bring me over and use me for the remainder of the half hour for your practice. And yeah, make some progress. Any questions? Also, you can email me if you're part of Team Learn at Home. And otherwise, thank you for showing up for your learning today. Bye.